Hi, my name is Andrew Ceballos, and I'm with the Stanford Optical Society. So I just want to start with an overview of our chapter's activities, or our chapter's outreach activities, to be specific. So we do a few different kinds of events. In the past year and a half, big focus has been less on classroom activities, more on large exhibiting events or smaller exhibiting events at schools. So we're every year at the Bay Area Maker Fair, Bay Area Science Festival, Discovery Day at AT&T Park. And at these events we see thousands of children, students, teachers, parents in a day, and we try to get them to come see our demos with some more flashy stuff like our laser maze and laser heart, which you can see pictures of here. But once we have them, we want to teach them a little bit of science, so that's where our smaller demos come into play. So we have our just a simple imaging system, which is fun for especially, well, pretty much everyone to play with, but kids especially love this. It's just the Mirage mirror imaging system. It's two mirrors that take an object down in the bottom, image it, make it look like a 3D object floating on top. And oftentimes people will confuse this with a hologram. It's really just an imaging system with mirrors instead of lenses. And we have a real hologram to show them what the difference is. Next, we have our Polariscope. It's a light source with a polarizer and then a rotatable polarizer at the top. So we use this to sort of, after we've introduced the idea that light is polarized or can be polarized, and what that means, sort of how you can use that. We have, in this case, just a pair of safety glasses, and we use this to show that you can see stress in molded plastic as a result of the birefringence in this crossed polarizer setup. And you can move that around by stressing the plastic yourself. Second, we've got corn syrup, which is optically active. So what that means is it rotates the polarization of the light, and this is dispersive, so it rotates each wavelength slightly differently. And if you insert it into the Polariscope and rotate the polarizer on top, you can actually scan through different colors. And that's just because each wavelength is polarized slightly differently, and then at the output you can scan through those different polarizations. Here is just a simple demo for light interacting with matter. We've got 3 laser pointers, 3 different colors, 405, 532, 635. First, we've got a pair of cheap, not really high quality laser safety goggles from eBay. And we can see here that it's meant for green, designed for green. It also blocks the blue a little bit. So what's happening here is the light's being absorbed in the blue and green spectral regions, but not the red. So without the glasses, with the glasses. We can move on to these collection of liquids here. We've got water with some coffee creamer in it. And if we shine the different lasers into it, we can see that they're all scattering, but we can see that the shorter wavelengths, the blue, green, are scattering more quickly than the red. So that's scattering is going to be inversely, it's going to be stronger for shorter wavelengths. Then we've got corn syrup, tonic water, and some Sprite with highlighter soaked into it. So in this case, we can start with the red laser, shine them into each of them, see what the effect is. Nothing particularly interesting in any of these cases. Then move on to the green, which causes no fluorescence, a little bit of scattering in the corn syrup. Same thing in the tonic water, and it causes actually the this highlighter solution to fluoresce. And if you might be able to guess that now the blue laser is going to make all of these fluoresce pretty brilliantly. And yeah, so just showing that as you increase the energy of the photons, you're going to cause fluorescence with more materials. Here we have some diffraction gratings. We use these to explain how diffraction gratings are used, or how light can be composed of different wavelengths, and you can measure that by separating them with a diffraction grating, for example. And something we haven't really incorporated into any of our exhibits or lessons yet is just this simple spectrometer we got off of Amazon that has a slit for viewing a light source on this end, and it's got a calibrated readout for the separated spectrum. And finally, we have this setup here that's the culminating activity in our geometrical optics classroom activity. So that's one of two classroom activities we do, and we're sort of revamping our lesson planning and trying to add more. But right now the geometrical optics is our main lesson that we have to teach students who come in from local schools. And what this is just these 3D printed holders that you can use rubber bands to attach lenses to them. In this case, 50mm lenses, or mounted slide samples mounted on microscope slides. And this is just a simple imaging setup that at the end of the geometrical optics class we have students try to build, and it's just simple infinity corrected there we go, infinity corrected microscope with about 3 times magnification. So yeah, these are the demos I have to show you today. Thank you. And